Yeah.
How?
We have a group in DC, but I think we should have 4 members, but only 3 in our group.
Yeah, because some people drop the
Yeah.
class, right? So
Uh,
if there is some group that is also has a few members, then we will merge them together. Don't worry.
yeah.
So did you guys talk to each other? Where did you talk to each other?
A little bit, and we have started to have some data
Mhm.
on challenge. It's going on challenge 0. Yeah.
Did you have a problem understanding the challenge? Did you understand the challenge?
I think it's yes.
It's pretty nice, right? Should be pretty good.
Yeah. So we need to have a presentation next week.
Yeah, exactly. Yes, around 20 minutes, everybody talks. Were you did you choose yourself as a leader, or were you selected as a leader?
No, I just saw my name
You just
on
saw
the
your name.
leader column. Yeah.
Are you excited to be a leader for this challenge?
I think it's fine. Yeah.
I can feel the excitement in your voice. I can feel that you're
Yeah.
very
Okay.
excited. Okay, very good. So exactly. So if some people are not answering to your email, to your messages, you can try to talk to them here during class. Huh? No problem. Okay. Group C. Is there anybody from Group C?
Hello.
Hello.
I'm the leader of Group C,
Very good.
and we
Let me
have
ask you a question. Because on the way you speak, I can already tell that you chose to be a leader, correct?
No, I'm selected.
Because you sound very excited, so I was hoping that
I'm nervous.
you are nervous. There's nothing to be nervous. Go ahead.
We created a group chat in line, and we've discussed over challenge 0 a little bit, and one of our member have almost finished level 1 of challenge 0.
So that's what you have to prevent, right? Because you guys have to work together, right? So of course,
Yeah.
if you take one guy, the guy goes on ChatGPT and he writes all the code and does all the loaders, but it's not interesting, right? I understand. Because some students they do that. Yeah, they tend to have their attitude because they think that they make their life easy for everybody. But yeah, try to get everybody to cooperate. Okay. Yeah.
Okay, we will cooperate the rest of the challenge.
Did you guys know each other from before, or
No, we don't know each other.
are you gonna meet physically? Are you just gonna talk online?
Online maybe. Yeah.
You guys can also get together, right? And talk physically to each other. But
Okay.
I
I
mean,
will
you guys
ask my member.
but you know, the weather is nice. It's not too hot. It's not too cold. You know, you can also sit somewhere.
Yeah. Yes.
Tell me.
Yeah. There's our progress now.
Okay, very good. So Group D, is anybody from Group D here? Group D. Jiang Xuesen, Group D here. Anybody from Group D? Anybody from Group D, guys? Let me check. Is it there? Lance. Anybody from Group D, guys? No. I will come back to the. Okay, Group E. Anybody from Group E? Anybody from Group E?
Yeah, I'm from Group E.
Okay, nice to meet you.
But I'm not the leader.
Okay. Because you guys are missing the leader, or?
I don't know if she knew she was the leader or not.
I think
not been communicated.
So you guys haven't communicated yet?
Yep.
Okay.
So maybe I will try communicate others and
Okay,
tell her
so-
the leader.
Okay, let's do this. So because you try to communicate with the guys now. Let's see if the other ones are also here. There are just too many names in the chat. I cannot. Yeah, see if some other people are in the chat now. Otherwise, I will try to merge. Otherwise, we merge some of the groups. Okay, we could
Okay.
merge you guys with group. Yeah, with some other group. Yeah, we merge from group A. I haven't heard anybody from group A. So group A is missing and group D is missing. So we could merge the guys somewhere. Okay, there's a question coming on. Go ahead with the question.
I think I'm group A.
Oh, you're from group A?
Yes.
Okay, so just a second, I'll get you to you guys. Okay, so group A is back. So group D still we haven't heard from group D. Just a second, then group D. Let me take a note. Group D missing. Group D missing. Okay, so let's go ahead with group E. So group E, try to communicate with everybody right now.
Yeah.
And then if you find the people, all good. If you find at least 3 people, then you're all good. Otherwise, I'll suggest to merge you with group D or group A. Let's see how it goes. Okay.
Okay.
Go ahead. The group A. Tell me everything about group A.
We have 5 people, including me, and one of our member is going to he's not going to take this course this semester.
Okay.
And the other another one, I don't know why I can't find his. I don't know how to contact him, and he didn't put his message on the Excel.
Okay, no problem. Then
So,
yeah, can I put you in? Okay. I'm getting a little bit confused because let me just do a quick document, okay? Because I was not taking notes so far, and it was a mistake. Each deck. So let's go through all the groups, and then we do another pass, and we see which groups we need to merge. Okay. PDL 2026. Okay, so we do. Let me do a document. Open to anybody. Okay, other question. Go ahead with the other question.
What does scroll back mean in the list?
What do you mean?
In the group division, there's a scroll back.
Huh? So there is this document, right?
Yes.
So there is this document, right?
I
Wait a
mean,
second.
no, I
Is
mean,
this
from the group division, there's member 1, 2, 3, 4, 5, and a scroll back.
Oh, just because we put 5 members, but the leader was not chosen, right? So the idea is that after the leader is chosen, then we do this. Hop, and we bring it down back. So you scroll back of 1. That was the meaning of scroll back. Yeah.
Oh, okay.
Are you just a second? Which group are you?
I'm group A, so I just.
Okay. Now we're finding the members slowly. Okay. Now we're finding the members slowly. So group D also find the member. Now I was just talking to guys. Too many things going back and forth. I was just talking to group E, correct? I was just talking to group E. Group F is group F here.
Hi, Professor. I'm a
Hi.
member of the group F.
Were you a chosen leader or were you a selected leader?
I'm selected.
Very good. Are you excited about this job? Are you excited?
Yes.
Very
I
good.
think one of our members are out of this course.
Okay.
And we take the field time to find each other's
Okay.
last weekend, and we don't have any idea until this Monday about this challenge. So we take a little time to discuss about what this challenge is about, and we now we have finished to level 2.1, and we're going to finish this uh, mm, in next Tuesday, I think.
Okay, very good, very good. Should be Wednesday, but anyway. So how many people are active then? 4 people are active, correct? Group F, you are four people are active, correct? Or 3 people?
We are now have 3 people.
Okay, 3 people. Very good.
And the 3
Then
is gone.
I understand. So let's go ahead and then we figured out what to do. Group G. Do we have a representative from Group G? Is the leader from Group G here?
Hello. Can you hear me?
Hello. Tell me everything.
Yes. We were 4 people. We had like organized. Oh, sorry, what?
Are you a chosen leader or a selected leader? Were you chosen?
I'm not a leader. I'm member 3 here.
Okay.
So essentially, my entire group dropped the course. So I'm currently alone. So that's why like I'm speaking.
Okay. Now we reorganize you. Don't worry. We'll put you in another group. Okay. Good.
Yes. Yes.
I'm going to do a second round so that first we hear from everybody and then we decide how to reorganize the groups. Very good. Group H. Is Group H here, guys? Anybody from Group H? Okay, Group H. How is it possible that everybody from Group H is dropped off? Okay. Group H, no sign from Group H, correct? Okay, good. Sort of normal, guys. After the first 2 weeks, a lot of people drop. So now we move to this document. Copy link done, and then I'll post it in Slack. Channel each deck document where we will record the progress in the challenges. Okay, we do a quick document here. Now we see where to merge. So this is, let me share here. So we do a small heading here, page tag, PDL 2026. Then we do a small, this is called the Meet Challenge report, challenge 0. Good. Now you can leave your comments, right? So now we are heading 2. We have group A, group B, group B, group C, group D, group E, F, G, H. Okay, so we're gonna drop some of these groups. So we're gonna merge some of them, and so let's do this now. So okay, group A, come back. How many active members?
3.
3 active members. Okay, so you found everybody. Okay, 3 active members group. Group B, how many active members? Group B.
3 member in our DC group, but I saw 4 on the.
It's okay. Yeah, so we're talking about active members, right? So some people.
I think it's 3. Yeah.
Yeah, because some people drop the class and they don't write it anywhere, so we just have to figure out who's active. Okay, Group C active members. Group C.
5 members.
5 members, very good. Group D active members. Group D is the one that was no. Group D, there was somebody from Group D, right? How many people in Group D? Let me check the chat. Group C, Group D. Nobody from Group D.
Oh,
there's.
I saw that 2 members don't fill in any information in the
sheet. So
right now there is you. Do you have somebody else, or is just you?
uh, oh, um, the other one is in the chat box. Like, so maybe two. Only
Two people. I think it's two people. Okay. Group E. How many active members in Group E?
Now we have 3.
3. Very good. Group F.
And now we have 3 active members.
Very good. Group G. How many?
1.
Come again. How many?
1.
1. Very sad. I'm very sorry. Group H. How many active members? I think Group H is 0, right? Group H. Nobody's active in Group H. Okay.
I'm from Group H.
Okay, so you just one. Just so did you guys try to communicate? Did you? What
Not
happened?
yet.
Can you try to communicate now and see if somebody else is around? Otherwise, I will merge your group with somebody else. Okay. So what we could do is that for sure we could merge group D and E, so we get to 5 members. We could group F and G, so we have 4 members, and we could merge H and A. It's just I'm not sure how many members are in group H. Let's assume there is at least 1. Okay. So I propose this. Propose. So we merge. We set D and E, merge D and E. Then we merge F and G. Then we merge H and A. Okay? What do you think, guys? So it's normal that people drop off after the first week. So we just, as I said, it's kind of hard to from here until the mid-semester, there are some people that are going to drop out. And yeah, so we have to adapt to this, right? So anyone that does not know what the group is, because we have 24 people in chat, right? And we have, if we do the merging, right? If we do the merging, we will have that. It should be okay. Yeah. Okay, good. Anybody that doesn't know which group they are in? Because there are 24 people. Then there's me, Simon, Naufal, and the AI assistant. So that's 4 people. So there are 20 people. So we should have eventually, if we merge 3 groups, then we should have 1, 2, 3, 4, 5 groups, or 5 people each, roughly. So we should be okay. Everybody should have a group. Okay, everybody should have a group. Any other question? Any other question? Please, guys, reorganize yourselves. Again, sorry that, I mean, that's why we have challenge 0, right? Because we know that some people will drop off, and so we have to adapt to this. Go ahead, guys. Any question? Only 3 people in group B. Only 3 people in group B. Yeah, group B is 3 people, but group B, I merge you, right? I see. So why didn't I merge group B? Okay, good point. So let's try to another merging. Let's discuss another merge. A plus B. Okay. So there will be 6 people. Yeah, because okay. Tell me which one you prefer. We could do another alternative. Could be. Okay, and then we vote. Version 1. So we have A plus H, group B, group C, group D plus H, F plus G, okay? Then we have V2, where we let we have so here the minimum group size is 3, okay? So we might want to have a minimum group size of 4. So if we do a minimum group size of 4, we will have A plus B, then we will have C, then we will have D plus E, F plus, and then we'll have F plus G plus H. F plus G plus H. And in this case, the mean group size is 4. Okay. Do you prefer V1 or V2? I mean, which one you prefer? I mean, I guess I should just ask the people in group B if they want to, but let's see what you guys think. Otherwise, I agree. I mean, V2 would be more desirable. Okay. Okay, good. Okay, very good. Very good. I see that there are some people that are happy to correct me. Very good. Good point. Good point. Okay, so this one here is decided. This one here is striking out the text. Where is the strikeout? Where is the strikeout text? I forgot. I always forget. Where is the strikeout text? Doesn't matter. Okay. So you guys do this, right? So try to communicate now, right? So that you invite the people to the whatever, to the line chat and whatever, so that after this class you guys can start working right away. Okay. Yeah, the logistics, as I said, the logistics of the class are a little bit of a pain in the neck, but now we should all be okay. Okay. Good. And if somebody else comes online later on, then we'll just add it to the groups that they've been merged now. Okay. Good. Any other question? So you guys can leave comments on this document, right? So this is not an edit document because later on I will record the score for the pitch deck. So it's you're only viewers. I'm the only editor, but you can just leave a comment if there is some mistakes. Okay. Good. Let me ask you a question. Do you want me to go through the challenge, or do we go to the slides? Question mark. C versus challenge. Okay, let's see what people want to do. Yeah. Okay, very good. I don't know if it's okay. Everybody wants to do the challenge. I don't know if it's a sign that the challenge is not written well, or if you just want to hear my opinion. If you want me to hear my voice describing the challenge, I hope it's the second one and not the first one. Okay, good. So the first challenge is just supposed to be a little bit of fun, meaning that we take this very cute data set, which is the Spotify track data set. Okay, so I don't endorse Spotify. I don't think it's a good app. I don't think it's a good service, but the data is collected maybe before Spotify became more of a problem. Okay, let me just suggest you something. Yeah, and the mood machine. Let me just suggest you a book, right? I think it's very. I mean, there are many societal changes that are occurring through this new technology that have been introduced. and we are only partially aware of whatever is happening. So this book describes the effect of the rise of Spotify and how people started using Spotify to modulate their mood. Anyway, don't want to go into this. See the interview with the author. It's a very interesting book. Anyway, this is to say, there is going off topic. We just focus on the data set. We don't care too much where it comes from. Okay, so it just reflects some listener preferences and all, and we go ahead with that. Very good. So it's a data set that they took on Spotify for a certain amount of years where they collected the data, and they collected 100,000 songs. Okay, and each song has 20 attributes. Okay, and there are also musical genre, and this is 125 musical genre. This is also something interesting. There is a specific identifier for the different music genre. And then you see here the features of the different tracks. Okay, so there is a unique identifier, there is a popularity, there is a duration, if there is explicit lyric, then they have these audio features that the engineers. Key, let's see who knows what is the key. Anybody knows what is the key? What is the key in this context? Let's see, who knows about the key? Anybody that has anybody that took music, took music. What is the key? What is the mode? What is the mode? Okay. So there are these features where the key, the mode, the time signature, and then there is the release year, and then the genre. So the genre is it's something that is a feature that the Spotify itself defined, and they have. I don't remember, but they have. I don't remember how many genre there are, but there are some. Basically, they are self-supervised. Okay, so it's self-supervised. Okay, very good. So then, if you, depending on where you get the data set, then you get different. There are different features that people have added because you can pool, of course, the information from other data sources in augmented data set. So see which one you like the first. I saw somebody posted a link to the Hugging Face, and then there are some information is also the ranking of the track, the stream numbers, and the date in which it was released. Okay, so you can. There is one on Kaggle, there is one in Hugging Face, and usually, so usually the data set stops at a certain point in time. Just be aware of this. So for this one here, we go back to the beautiful chart that we had about data, right? Data exploration. Okay, so once you get the data is being curated and is being cleaned. So now we have to discuss how to explore the data. Okay. So of course you put it into a nice data frame in Python, and you expect the distribution, or you expect some of the high-level features of the data set. So first of all, you can do some summary statistics. Okay, so for example, here you can do the popularity, right? So you can see, for example, what is the popularity, the distribution of the popularity in different decades, in different years. You can see if, for example, the average ranking, right? If the average popularity of a song goes up and goes down, because of course there are more songs that are being released as time passes by, but the number of listeners does not increase. So you wonder if what happens is that the popularity peak spreads out, meaning that there are more songs that are popular since more songs are released, or if there is the rise of these super international artists that have billions of streams. So actually, even if the total amount of songs that is released is large, then the peak of popularity becomes smaller. Okay, that's something that's a research question that it's in your mind, right? That's something that you would want to try to represent. For example, the distribution of the audio features, right? So you have this danceability, energy, tempo, so on and so forth, and you can do a plot of this feature over time, and you can be like, oh, his music getting faster or getting slower, right? So, for example, we know that people don't sit down and listen to tracks in the living room anymore, because now we have phones and computers and VR glasses and treadmills in our living room. So people don't sit down and, like in the 1960s, to just listen to an audio for an hour. So does it mean that the speed of the song is going faster? That people like more danceable songs because now people are more commonly dancing, something like that. Okay, so you have to pose this as a sort of question. Huh? Then again, how many tracks per artist, right? So artists producing more or less track as time passes by. So all these different things that you can do when you take your data set, you divide your data set in, for example, chunks of 5 years, or chunks of 1 year, or chunk of 10 years, and then you have a plot for the average features every 5 years. Very good. Then visualize the stuff. So visualize in histogram, box plot, box chart, scatter plots. So this is something that you understand. Then some intermediate trends, right? So you can try to identify some temporal trends that we were saying, changes throughout the different decades. You can try to get the popularity of a certain genre by seeing the number of releases and correlating the average popularity of a genre. So you take the genre. So this is a classification, let's say 10 classes, and you see the popularity of a certain genre. So you can see if there are some genres that are more popular than others. For example, you expect pop to be more popular than classical music, and hip hop to be more popular than jazz. So does your intuition, can your intuition be validated in the data? Then see which one you get, and then you can get the Spotify top 200 weekly charts from some other data source, and then you can align the features so that you can see, for example, some temporal trajectory, right, let's say, in the popularity of a song through time, right? So now we have the impression that songs are popular for a shorter amount of time. Can you validate this in the data, right? So if you merge the two data sets, can you see that the most popular song in the 2010 were popular for a longer period of time than the most popular in the song in the 2020s. Okay, some research question like this. So this is very, it's very individual how you do this, right? So because you will notice that when we design the challenge, right, we try to make the challenge in a way so that everybody can have a different approach or a different interpretation, right? Because if I write a challenge with very specific points and very precise entries, then all the groups are going to have the same set of output. And then when the groups present in class, then we have 2 hours in which everybody says the variance of this variable is this, the plot of this is this and this and that. So try to personalize your challenge, right? Try to do something that other people haven't done, because remember that the challenge is scored by other students, right? So you have to do something compelling for other people to do. If you do exactly what they did, then when they read your challenge, then they think it's boring because they did it as well, and so on and so forth. And also be aware of the following, that if you ask ChatGPT to help you with this, ChatGPT will give the same suggestion to everybody, okay? So it is not uncommon that people are lazy, or they don't find the challenge interesting. So either it's your fault or it's my fault. It's somebody's fault. So what they do is that they just sit down and they feed the document to ChatGPT, and they ask ChatGPT to do a certain part of the challenge. But ChatGPT, if you don't add your understanding of the challenge, will just give the same output to everybody. So 2 groups that did the same approach and they just took the challenge and paste into ChatGPT, they will produce the same presentation. And then it's clear to everybody in the class that the students were not compelled to work on the challenge, and they just did copy and paste. And so the presentation is just uninteresting, right? Because people would have already seen this. Okay, back on topic. So this one here should be interesting, because you have to take 2 data sets and merge the 2 data sets. So the song identifier is unique, and so you can align the data set that has all these rankings and the weekly charts. Okay, Now, again, some more stuff, right? Compare stuff across decades, see which features are popular there, and now where it gets interesting, right? So you can do some clustering dimensionality reduction, okay? So now you guys have, some of you guys took my course, some of you guys haven't taken my course on machine learning. So if you know what is PCANT SNE, just go ahead and use it here. If you don't know, then go and try to learn it. So you can do some dimensionality reduction, and then you can do some k-means clustering to do the following, right? When the song is given to you, it's labeled with a genre. But as we said, this general label is semi-supervised, meaning that some people went and chose that one of the genre was, for example, jazz, and one of the genre was classic music, one of the genre was rock. But this is semi-supervised, meaning that some people chose some of the genre, and then they look at the data and they figured out that there are some subgenre that don't have a name, and so they just gave it a name. But what you can do is that you can take the features of the song without the genre, do PCA, 2K means clustering, and then you will find some clusters that may or may not correspond to some of the labels of the genre that are available to you. So you can ask yourself, oh, is there some subgenre that was not identified? Or is there a song which is really a cross between classical music and hip hop? Is there really a set of songs that are really a mix between funk and hip hop, something like that? You will see this if you do this k-means clustering. Very good. Then so can you do a classification? Okay, so let's say that you have to predict whether a song will be charting or will not be charting. Okay, so now we go back again to another classical ML topic, which is classification. So let's say that you have to build a predictor that looks at the song's features and try to predict whether the song is going to be a hit or not. Okay, so of course the speed, the tempo, the timing in which was released, you can probably predict with maybe with 20% accuracy whether a song will be a hit or not, based just on the 20 features that are provided. And for example, you can see like which artists are very similar, produce very similar songs, which artists have a very different song. Does an artist that have very diverse song achieve high popularity, right? Because you can assume that people preferences, they are along a certain axis. So if you're an artist, you can either choose a genre and produce the best song in that genre, or you can have a wider set of genre and see if you can capture a larger audience doing this. Then you can do this, right? So something that I want you guys to learn is as follows. You go on GitHub, and on GitHub you look for a certain model, a certain pre-trained model, and then you just apply this pre-trained model to your data, and you see what the output is. Meaning, there are some very good models, right, that they produce some very accurate outputs, and you should learn that if you need a certain output, if you need a certain, let's say, augmentation of your data or a certain processing of your data, you just go on GitHub, you download the model, you use the model. Okay, so learning to do this, it's very important. And so here I suggested the following. So you can go and give a song title to this API, and you can get the lyrics. Okay, so this is something that that works probably with all the songs released in the last 20 years. And but then what you can do is that you can put this into sentiment analysis model. So there are some very good models that they take a piece of text and they tell you if this text was happy, was sad, was reflective, was critical, was about love, was about war. So you can take a sentiment analysis model, right? And then you can use this as an augmented feature for your data set. And you can say, for example, songs that are about love, they have a better performance in the 2010 than in the 2020s, something like that. And then, of course, the chart position dynamics. Okay. Good. Something else. Yeah, the rest should be okay. That should be okay. So there are some questions here. Yeah, good. Any questions about the challenge? Any question? Any further question? Any question? You can ask in chat or ask me here. What I want to add something else.
Like where can we get the data?
It's here in the chat. Oh, so you just here. You see that somebody posted a link. So you just when you did the data set, you just you just type the name in Google and you find it. Right. Just here. So this type of data set, you find them either in Kaggle or in Hugging Face. So you must know this. You must know this website, right? You might not know that Google owns Kaggle, right? So Kaggle has like 8 million visitors a week or something. There's a crazy amount of visitors, but it's it's a great website. So whenever you need a data set, you see, so they host a bunch of competitions and they also have a bunch of data set. So that's also a point of pride, right? If you have a data set on Kaggle or on Hugging Face, that means that you have really contributed to the community. Okay, any other question? Go ahead. You don't need to raise your hand. Just tell me.
Actually, I found some data, but actually there are no dates. Many of them don't have dates.
Where did you get it? You get it from Kaggle or you get it from
Kaggle and Hugging?
Come again?
Both don't have the dates.
Oh, both don't have the
data with that big ones. Like
there's no release date. That's what you mean?
Most of the data don't have a release date.
Do you know what's a portion that doesn't have a release date?
Like what I found is on Kaggle and it has like 1997 to 2023, but it's a big data, like have like 11,000, but however it does not have years. But some data that have years, it's like only have 2023.
I see.
Yeah, so
let's see if there's
level 2.
Yes.
The task that need years, they cannot do.
So in the case, you can decide what to. Okay, so let's just check together. Can somebody? So is there somebody that found a nice data set with days complete with the release date? That's it. Pom. So because like the Kaggle one, okay, let's just show this. I have to say that your microphone is a little bit of a potato. God damn it, it was so hard to hear what you were saying. The quality of your mic is a little bit terrible. So this one here, you say that doesn't have the features, doesn't have the release date, track ID, artist, album name, track name. What are the other features? Show me the other feature. 21 columns. Unique values, duration, popularity, energy, danceability. I agree with you. There is no release date.
Yeah, the other one on the Hug Face is also don't have that years.
Okay, very good.
It's the same data.
Yeah, it's the same data, of course. So that's the weave. Then we put weave release date. From track album release date. So why does this guy say that they have it? Where's the release date? See, it says that the release date is there, right? It says that it's there. Descriptive features such as song include information about the song, such as artist name and release date. So does this one here has the release date? Let me check. Genre is here. Energy. Columns. Energy, tempo, danceability. Some guys, help me out a little bit, huh? Descriptive features. Yeah, no. This one here should have the descriptive features, right? So this data set here should have the release date. Where is the tab? Where is the tab? Where is the tab? Where is the tab? Yeah, this one here as the descriptive features is the release date, right? Can you confirm? Yeah. Is it the same data set or not? Yeah. Can you check this one here? The release date should be one of the columns.
Yeah, like but the size of this data set is just kind of small, and
Well, then let me check. What is the size? Pop, 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 pop.
It's like high popularity Spotify data, so it only captures the high popularity.
Very nice, very nice. So what you can do then is that you can Spotify API release date. So because the other thing that maybe you can try, okay, is to use the API.
Or to capture it by themselves.
Yeah, you can try.
Okay.
Of course, you have to limit yourself, right? You cannot have an API. But we'll check the API before. Let me check. Have you used an API before? Question mark. Because some of the students here are from engineering, so they are not familiar with APIs. Yeah, you see that you can have an API. Yeah, you can get the album release. So you have 50. Yeah, you have a 50. You have a range of 50. Yeah. No. Get album. Get new releases. What is the get release date? Artist, audiobooks. Library. Well, concept tutorial, how to's. Client credential, blah, 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 how to's, how to. Change log. Okay, we will figure out, guys. We'll figure it out. Get release date in Spotify here. Let's see. Wow. Oh, nice. Okay, good. Look at this Stack Overflow. This Stack Overflow answer. Oof. Okay. You can use this Stack Overflow answer. They say, and they tell you how to get the API in Python. Because there is also yeah, how to release electric summer. Okay, so try to do it, guys. If you get stuck, don't worry. But yeah, so there are different ways of doing it. Very nice. Good. Okay, let me see how you solve this this problem. Any other question, guys? Okay, very good. I suggest we take a 5 minutes break. So I'll see you back at 7:20. Then I want to do a little bit of presentation of gradient descent. I'll try to keep it short since since probably hopefully from next time on there is going to be more student presentation, less me talking. But yeah, so let's take a 5 minutes break and I'll see you back at 20. Drink some water, walk around, stay active. Okay, I'll see you back in 5 minutes, guys. Hey guys, if you have any question, you can ask me. Yeah? So it's a couple of minutes, then we start. So somebody wrote me on Slack. Yeah, just since we are in a break. So have you seen this Suno, right? Have you seen Suno, guys? Because Suno is the song generation AI, and Suno made a deal with Spotify so that some artists they can lend. Okay, it's a longer discussion, but basically now this music generation models, right? They can generate songs, right? So a lot of people on Spotify, they just go and they make music using Suno, and then they just monetize. And Spotify has made no effort in curbing the AI onslaught to their submission. So like real artists are being completely overpowered and overnumbered by AI music, and it's pretty normal now that you go to the most listened Spotify songs, and then you look at the top 10 releases, and 1 or 2 releases are from AI. Okay, because then people go and when they create the song, then they create a virtual artist, and it's a lot of discussion in the space because of course people are monetizing AI outputs and taking money away from real artists that play real instruments, that live real life, and they need real bread to eat. And so in order, Spotify has done nothing to curb this, so they don't particularly try to block AI submissions. And what they're doing now also is also partnering with some artists, because they have the idea that if an artist agrees, they can personalize a model to sound exactly like your favorite artist. So if you want to have a song of Justin Bieber that sings about how beautiful you are using your own name and surname, then you can generate it, let's say legally. Okay, because they know that these models, they've been trained on copyrighted data. But of course, like nobody prevented them from using copyrighted data, right? There was no legal mechanism that prevented this model from being trained on copyrighted data. And we can discuss how this model are trained, right? Because of course it's an American company. They cannot train it on American soil because otherwise they will be subject to American law. So this type of company, they send out their model to some computer farm in some country where copyright regulations are not so strict, and then they let the model train in these servers outside of the strict regulations, and the model comes back that he can create the perfect song from Justin Bieber. But then if somebody asks them, oh, did you use copyrighted Justin Bieber material in order to train the models? Like, oh no, but we didn't. We just sent out the model to be trained to this server farm, and we don't know how the data was collected. So it's very, very shady, right? It's a very shady situation. Okay, this is to say, I don't many things to discuss. Okay, any questions? Otherwise, we do some SGD presentation, some presentation SGD, and then we move on with our life. Okay, any comments? Anything about the challenge? Any questions? Yeah. Okay, good. So if there is no question, then we go through a little bit of SGD, and then we move on with our life. Although I think to begin with, not many of you guys use Spotify. Let me screenshot. Do you use Spotify? Question mark. you used Sumo before 2/3. So I use Suno all the time to make music for my baby, because it was also multilingual. So yeah, so very interesting. So nobody has used Sumo. So yes, okay. So yes is two, right? Yes is two. Some people use it. I think you guys have some other service that you prefer. Okay, so let me just share the slides. Okay, so finally somebody that they used it. Okay, I have to share the entire screen, guys, because I was not able to figure out that, yeah, there's some issue with my screen. So let me go in full screen mode. And full screen mode, where is it? I cannot go in full screen. What is happening? There is some update that I have to do. At the moment, I cannot do full screen. Okay, let me just check that you can see it. Okay, so yeah, you can see it. Good. So where we stopped last time were as follows. We described the architecture of a deep neural network. We say, oh, we can represent this with different layers. We have weights between the layers. We have a bias. But this is not the end of the story, right? Because this is just the structure of the network. So it describes the type of operations that we can perform, but we know nothing about how to train it. Okay, so how to make it perform a task that is interesting for us. So in order to do this, we have to do gradient descent. Okay, so we need to calculate the derivative, and in particular, we need to calculate the derivative of the loss with respect to the weights at different layers. Okay. And then this operation has to be repeated for all of the elements in the data set. So we have to sort of accumulate gradients across the different elements in the data set. Okay, so of course we are talking about AI. So if somebody asks you to do a derivative, then you will use Wolfram Alpha. If you don't know what is Wolfram Alpha, look it up. The history of the guy is pretty amazing. So we said that we develop deep neural networks starting from logistic regression, so we can look at the derivative of in the logistic regression. And I will bring your attention to the following. Okay, so the ingredients that we're going to need is this. So you have a function y, which is a g of x, and then you have function z, which is an f of y, which is the f of g of x. So this is a composition rule. Okay, if I want the derivative of y with respect to x, then there is this what people call, well, I don't know, there are different names, like the cross-out rule or the cancellation rule or whatever, different names for different contexts. But basically, if you want the derivative of z with respect to x, this is the product of the following two derivatives: derivative of z with respect to y, derivative of y with respect to x. So this is, sometimes you call it the cross-out rule, because you see that the partial, right? If this was a fraction, then you are canceling out the partial as you do in a fraction. Okay. Okay. So this is the first one. This is the composition rule. And then you have to ask yourself, what happens if now y is a vector and x is a vector? Vectors do not scale us. What we do is that we have the partial derivatives with respect to an element in the vector. So the derivative of z. So again, y is a vector and g is a function of a vector. So this is a vector function. Right? So you have usually the function that we describe a function that goes from maybe from r to the n, from a vector to a scalar, but this is a function that goes from a vector to a vector. So imagine this as a function which is applied component-wise to the elements of y. Okay, so we have a vector y, which is a function g of the vector x. Then we have the scalar z, okay, which is the function f of the vector y, which is the function f of the function g of the vector x. Okay, so all the dimensions work out. Don't worry about that. But now we want to do this. We want to take the derivative of the scalar z with respect to the vector x. Okay, in order to do this, we're going to produce a vector in which each entry of the derivative vector of this nabla vector is the derivative of the scalar z with respect to the entry I of the vector x. And how does the chain rule apply there? Okay, so this apply in a way which is a little bit expected. So you take the partial derivative of x with the partial derivative of yj, where j is a position in the vector y, and then you take the partial yj and partial xi. So it's a little bit like when you take a matrix time vector, right? So you have all the elements in the vector y, they multiply for all the partial in the vector partial yj, xj, xi. So here the z is fixed, the I is fixed, and the summation is over all the possible elements in the vector y. It's sort of what you would expect to do. And remember, of course, that if you have longer compositions, then you will just stack more summation, right? So let's say that you have find the z, the scalar z, which is a function of the xi, but in intermediate we have, let's say, a g1, a g2, and a g3, and a g4, and then this would be all the stacking of the partial derivatives. Okay, good. So now we said we start from logistic regression, so we are doing classification. So what we have here is a loss function, is binary cross entropy. Okay, so we have that the true label was yi, and the model produced the pi. Okay, so the pi is the probability that the output is 0, and the 1 minus py, sorry, is the probability there is 1. So if we were in the logistic regression case, then we will not have a deep neural network, and we will just take the derivative of our function yi with respect to the omega t. Okay, the omega transpose is the vector parameters. So what we do here is that we take the li and we just split it into different parts. Why? Because we know that the derivative of the sum is the sum of the derivatives. Here we have a log of an exp. We know that something nasty could happen when we take the log exp expression. So we just feel safer and split it into parts. So we have the loss component I and the loss component B. Sorry, guys. So when we take the derivative with respect to the omega, this w, okay, so this w is the parameters of our logistic regressor. Then we know that this will be the summation over these two losses, and plus we know that we have to accumulate the loss over all the elements in the data set. So this I ranges from 1 to n, and n is the size of the data set. Okay, very good. Then we have to take the derivative, and this table here, it's here not because this derivative is complicated, but it's more to explain to you how derivatives are taken in a computer. Okay, when you have a computer, when you have in Python, okay, operations are written in different lines of code, right? And when you call a function, right, you can create a function with which you associate a derivative. Okay, so if you write in the Python code that your function is minus yi log of 1 over blah blah blah, and then you ask the derivative with respect to y, Python will know that if this is the function, this is its derivative, and if this is the chain rule, this is how you compute the derivative. So there is a current automatic computation of the derivatives. Okay, and that's one of the very useful things that you obtain, that you can do this, and this is called autograd, like automatic gradient, because you just write the function and Python really knows what is the gradient. And now how is the gradient computed? Well, Python goes through the function and see how it's composed, what is the order of operation, and then he has a chain, right? There's a chain of operation. From this chain of operation, using this beautiful composition rule, it will compute the gradient automatically. Very, very useful. So when we have to do this computation, we have to think how Python thinks. So what would Python do? It will break down this operation in the following one, right? So first you start with the multiplication of the omega with the x. Remember that we're taking the derivative with respect to, always say omega, with respect to this w, okay? We are taking derivative with respect to w. So the order of operation is this: we take the w, then we exponentiate, then we sum 1, then we do the ratio, then we take the log, then we multiply by y1, okay? So imagine this as operations in your Python function, so that when you call autograd will know that you have to go from here to here, right? So it will know what are the derivatives. Okay, so operation first, the first partial result, xi1, and don't let this confuse you. You're taking the derivative of a matrix times a matrix. This is equal to minus x. So this rule is kind of there. Then you're taking the exponent, right, of vector times a vector, right? So e to the xi, then the derivative is this. So when you compose e to the xi1 derivative with w with e to the xi2 partial xi1, then you're just plugging this in the exponent. Then you have the next step, you sum 1. Of course, the sum 1 doesn't do anything. Then you have the ratio. When you have the ratio, you have this 1 over minus 1 over x squared term. So you go through this set of operations, and it comes out that the final derivative is just the composition of the derivative of all the intermediate results, and this is the value of the derivative. Remember, this is, again, a function that produces a scalar and takes a vector in input, okay? So when you take this partial derivative, it's partial derivative with respect to this w is a vector. So if you take the derivative of a scalar to a vector, right, this will be a vector that contains in each position the partial derivative of the loss function with respect to one of the entries of the vector. Now here there is an I. The I indicates that this is computed for the dataset row equal to I. So you have a yi and x. And then this partial derivative is accumulated all over the dataset. Very good. So this is the same story for B. Nothing changes. So if you understand the previous slide, you understand this one here. And then we have to understand what are we going to do with this derivative. So here we're doing gradient descent, right? So we are just taking a function, evaluating the function over the certain point, and then we proceed in the descending direction of the gradient. When we do this, of course, we have to choose the step size. Okay, well, how we're going to choose the step size? Of course, there are two regimes that are the obvious regime, and then we want to be in the middle of these two regimes. What are the two regimes? The regime in which the step that we take is too small. Okay, so the way in which proceed with SGT is very, very small. So the minimum is here, and we are taking very small steps. So we have to do a lot of computation in order to get to the minimum. Very undesirable, right? So if you take a step which is too small, then you are wasting a lot of computation, because your computer is there chunking and churning and churning and churning, and the result is improving, but you're so far away from the final result that you're just wasting electricity. So what you do, so you crank up your step size, and now the following happens. The minimum is here. You take first step, second step, third step, fourth step, fifth step. So you keep alternating between being far away, between different sizes of this descending cone toward your minimum, right? So you're not proceeding in a steady way toward your minimum. So if you look at your loss is oscillating a lot because you're taking very large steps, and you're not proceeding steadily toward the minimum. You're just jumping left and right, and probably getting stuck in some point which is far away from the minimum. And then there is the the best way to go, which is to just choose the right step which proceeds in a small number of steps to the minimum, and it gets there with no problems. Of course, when you approach a learning problem, you don't know which regime you have, and so usually people take the learning rate to be 10 to the minus 3, and then you play around with your profiler in order to find what is the best learning rate. Okay, and how does the profiler know what is the best learning rate? You see this. In one regime, your loss is decreasing very, very slowly. In the other regime, there is very large oscillation. And this is what you want to see in all your training, right? So you start far away from the solution, then your gradient descent finds a good descending direction, and then it blocks down. Okay, let me check if there is any question in chat. Sorry, guys, I have to, it's not right here. I have to start the computer. Okay, no questions. Go back to the presentation. Very good. So there are many ways in which actually one can dynamically change the learning rate as the iteration proceed. Usually one doesn't have a constant learning rate. You have a sort of decreasing learning rate, or maybe you have some adaptive learning rate. You don't use the vanilla version of SGD. You have some variance reduction technique. We're going to see this later. Now there is the second big question. So when we have a function, ideally there is we have the function on the left. Most likely we have the function on the right. So on the function in the left, what do we do is that we have a nice function which is conically, shaped, and it goes toward the minimum. And so wherever you initialize your SGD, right, you're always going to end up in the global maximum, and that's the end of the story. Okay. But in actuality, usually your function has many local minima and just one global local minima. Meaning that if you start from here, then SG is going to bring you to this point. If you start here, it's going to take you to this point. And if you start here, you only if you start from this initialization, then you're going to end up in the global minima. And this is why once we do an optimization, then we never take a single starting point and do SGD only once. We start with multiple initialization, and we try to see what is the best result that we obtain. Of course, neural networks, they end up in this regime, right? And the reality is that when you initialize, the space of initialization is so large, usually, because neural networks, they have so many parameters that if you randomly choose any of the values of the parameters, you could end up anywhere. And so it's like finding a good initialization, it's really critical. And that's why whenever possible, we don't randomly initialize a neural network, but we take some state of the neural network, which is already known to be a good starting point. Okay, so let's say that you're training a network that does a classification of cats versus dogs. Then you will take maybe a network that is being classified for, which has been trained for classifying trees versus roads, and you will take this network as being your starting network because you know that this network has learned some interesting feature processing that might be useful when you do your when you train your own network. And this is what we refer to as fine-tuning, meaning that we don't start from scratch. We start from a certain state and then we tune it to our specific problem. Okay, so once you get to SGD, you have repeated this a few times, you get a few minima. So what would you do? Of course, you can restart the algorithm. This is very costly because, let's say, if you have a network that takes 3 days to train, if you have to restart it again, it will take you 3 other days. So it's very expensive. So what you can do is that you can perturb the loss function in order to move the function away and see if really the training always go back to the same local minima. Yeah, so then a discussion is as follows. So we said that when you compute the loss function, you have to calculate the derivative of the loss function with respect to the network parameters with respect to one dataset entry, which is the dataset entry I, and then you sum these gradients for all elements in the dataset between I and n. Now, you saw the dataset with which we're working now, which is 100,000 samples. Of course, if you train a larger network, you need a larger dataset. So the larger the network, the larger the dataset. And let's say that the number of iterations that you have to do is in the order of tens of thousands before convergence. So in actuality, you do not need to compute the gradients of the full dataset because this will take too much energy, too much computation, and you're happy to do this. You take an approximation of the gradient, which you obtain by subsampling a small fraction of the dataset. Now, it is clear that this reduces the complexity, and so you must pay a price in reducing the complexity, which is the gradient that you obtain is a noisy gradient, so it doesn't go exactly in the direction of in the descending direction of the function, but it perturbs some noise. Now the question that you have to ask yourself is, if I just look at the sheer amount of computation, is it better to do 10 iterations with full precision gradient, or to do 100 iterations using 10% of the data set each time? Okay, and the answer 99.9% of the time is that the second option is better. Okay, because you can think of it this way, right? At the beginning of your iterations, right, of gradient descent, you are somewhere far away from the global minimum. So if you have a good direction, this good direction is already good enough for you to approach the minimum. If you have a very precise direction, that doesn't buy you too much, because you still have so much, let's say, so much space to go, right? So much updates to do, right? And so it is well understood that you choose this B, which is your batch size. And once you choose the batch size, it's always good to repeat many iterations with a smaller batch size than fewer iterations with a larger batch size. Okay, just be aware of this. The choice of the batch size, of course, it's sometimes critical. If your batch is too small, then you're not computing a precise gradient. If your batch is too large, then the computation takes too long. So you're always, teeter-tottering between these two aspects. Okay, good. Let's do another one. Any questions on this? Just want to check if there's any question. Any questions? Any questions? Again, sorry, I have to restart my computer to fix the sharing issue. macOS updated, and I have to update something else. Okay, if there are no questions, we do 10 more minutes, guys. I really feel I talk too much. And I go off topic often enough. Okay, good. So we did this, right? So we said we have the affine function, blah, blah, blah. We find the derivative. This is the partial derivative there. And now we have to describe, right? So from this one is the step that we discussed so far. We did everything for logistic regression. We did the discussion on the mini batch. We did the discussion on the partial derivative. We did the discussion on the chain rule. But when we have a neural network, we have to sort of route these derivatives throughout the different neurons, okay? Because the different neurons are connected with certain matrix omega. So we have to, we have to figure out how is the derivation of the derivative. How is the derivation of the derivative? No better way to say it. Perform when we have multiple neurons which are stacked in different layers. Okay, good. So we know that this has to be very elegant, because we know that we can train networks with thousands of layers. So there should be some trick to do this. And so we're going to see the trick today. Okay, we go down. And the trick that we have must work with different connectivities, okay? Because we know that we can connect the neurons in any pattern we want, and everything always goes through. Good. So we go back to what we were discussing before, that if we want to write a program that really can generalize across multiple architectures, then we have to have a way of writing the derivative which is sufficiently flexible, sufficiently efficient. And remember always that somebody gives us an X, somebody gives us a Y. Once they give it to us, they are fixed. The input complete loss between the true Y and the Y hat that we produced, and then we have to take a derivative of this loss with respect to the weights of the net. Okay, good. This is what we saw before. Then if you put the true variable here, it goes through. And this is the same table that we had before, but now the only difference is that we have put a true value to the value x. Okay, so let's say that there was a true x and a true y, and when we go back to the table that we had before and we substitute these values of x and y, then when we take this derivative, these derivatives are going to give us a number. Okay, so what we were saying before, that we think of the decomposition of the function in terms of composition of functions for which we associate a derivative. Now you have to believe me, and you can also check yourself, that this is also a computation paradigm, meaning that if you go back and you put a true value y and a true value x in that computation table, then the derivative numerically is going to give you the derivative of these two values. Okay, good. So we can get a true value there, and so this is how you do it, right? So you have the function f, and then you have its derivative. So you see if the function is a constant, then the derivative is going to be sorry. If the function is x, then the derivative is going to be 1. If the function is a scalar multiplication, then the derivative is the coefficient. If you have exponentiation, the derivative is also exponentiation, and so on and so forth. And you believe me that what we do is that we can build a computation graph, okay? And the computation graph will be something like this. If this is your x and this is your y, right? You can say that you have all these partial intermediate results which are obtained by applying one of the specific operations. So, for example, here there is multiplication, here there is subtraction, here there is exponentiation, here there is summation, here there is the one, here there is the division, there is the log. So we broke down the computation of this beautiful function, here, right, into application of elementary function for which we know the derivative. And then once we have this graph, we know how to go from x to y. And so then we can specify the structure of the computation. And as the computation proceeds from the x to the y, then we can also reverse engineer and go from the y, right, from the computation of the loss back to the derivative of the loss with respect to the coefficients. Okay, very, very, very good. Okay, so this is the computation graph that goes from the x to the omega to the y, and then back again. Good. So each node of the graph has two functions. One is to evaluate the variable and evaluate its partial derivative with respect to the previous variable. Okay, so everything is expressed in terms of partial results. We just stack the partial results and take the derivative with respect to the partial results. Then we can go either forward or back. So if we go forward, we compute the function, and we go and we produce the prediction, right, from the y to the prediction of the x. And then if we go backward, then we compute the derivative of this prediction with respect to the input, and then we try to improve the prediction so as to minimize the loss. Good. So this is the forward pass, the forward mode. We go with the omega is fixed, and we put in the input x. We get the input y, and given x and y, we compute the loss. Okay, so the forward mode, the network is producing your prediction. Okay, so here we're doing training. Okay, when we will not do training, then we will use inference. So we put in the x and we look at the result y. So in the forward mode, the network is not being used, it's not being trained. So the omega is fixed. You put in the omega, the network produces the y, and your expectation is that this y, this predicted y, is close to a true y. Okay. In the backward mode, actually we are looking to update omega, and we know x and y. Okay. So we go forward from the x and the y, right, and we store some of the intermediate values of these intermediate results. Then we compute backward the derivative of these partial results with respect to the derivative of the loss with respect to these partial results, and then I multiply everything together according to the computation graph that we have. We obtain the partial derivative. Very good. Okay. So this is it's kind of hard for you guys maybe to believe that this is really an exact compilation of the gradient. You can do it yourself with some simple function, and you can convince yourself that AutoCAD really works. And the other thing is that when you write, if you want to write some custom function in the DNN, it is very easy for you to implement the derivative yourself. And so if you write some custom function, then you can just put them. You just put them in the network training, and you can have your custom layers, your custom activation. Your custom activation function using your own AutoCAD, right? So the graph computation is perfectly modular, right? So you can write a function that has a certain derivative. You put it in the correct way into PyTorch or TensorFlow or whatever, and you will see that this computation is exact. Okay, let's talk a little bit about optimizers. Momentum and adaptive learning. As we said, the bane of our existence in deep learning are local minima. So because if you end up in a local minima, you don't know that you are at the local minima. So in a sense, when you train a network, you never know what is the true potential of the network until you have explored the space of solution fully. Okay. So the nice thing about neural networks in general is that even if you are in a local minima, people you live well in a local minima, right? So you don't have to really strive to find the true local minimum. For most network, if you end up for most neural network, the idea is that they are heavily hyperparameterized, meaning that there are many parameters in neural networks, and millions and millions of parameters, hundreds of millions of parameters. So if whatever learning problem you are solving, it is usually true that there are different networks that can solve the problem well, and the difference in performance between these networks is not as critical. Okay, so there are many networks that you could land up with your optimization that will make you happy enough. Okay, so there is no need to really find the global minimum. Okay, so people have studied this problem of how hard it is to run SG for a long time. And there is this idea that we look at the Hessian, so the second derivative of your gradient, which is going to be a matrix. And from this one here, you can get a concept of curvature. Okay, so you look at the Hessian, you look at some eigenvalues, and you can obtain an estimation of the curvature. And if the Hessian is very curved, right, then a small change in your parameters will have a drastic change in the loss function. Okay, so the gradients will change a lot around a small perturbation of your weights, and this is not desirable. And here the choice of the loss function is critical, because you can choose some loss function that don't tend to not have this behavior, and instead give you a nice smooth performance. Okay. So you see, we go back here, right? So you see that if you take this loss function here, I don't know which loss function it is, but it's very smooth. If you had to take a very sharp loss function, then the sharp head of the loss function will result in a very Hill condition training. So it's not desirable. Okay. So for example, you can imagine that this is what happens if you want your network to, for example, to output some zeros and ones, right? So let's say that you have a sigmoid activation function and you want your network to output zeros and ones. It's clear that in order for the network to output a value which is only 0, only 1, you have to take a continuous function and make it very sharp. And as you ask the network to be sharper and sharper and sharper, this will produce Hill conditioning. And Hill conditioning means that small perturbation of the weights will produce a big change in the gradients. And so they're a really hard network to train, because you have to take a very small step size and try to stabilize the training. Otherwise, you will jump from solution to solution, as you see here. Good. So if you have a very sharp function that you still have to train, right? Because sometimes there is no choice on what you need to do with your network. Then you will have this type of situation that you approach the cliff, and then you jump, and after you jump, there is a very large gradient. The large gradient kicks you, punches you down, right? It kicks you out again from being able to learn the parameter here. Okay, so what you do sometimes is that you have to clip the gradient. So you say that if the gradient is larger than some values that I decided, which is u, then what I'm gonna do, I'm gonna scale down the gradient to have a maximum size of u. So here I take the gradient and I divide the gradient by its norm. So I make the gradient unitary norm, and then I multiply by u, which means I keep the direction of my gradient, okay, but I bring down the magnitude to be at most u. Good. So sometimes, as we said, we take a large step size, and because we need to approach the solution with a certain speed, because maybe we don't have computational resources. So let's say that we are in this regime in which we have large oscillation in the gradient values, and we have no way to, let's say, to curb down this oscillation by reducing the learning rate, because that will take too long. So what we can do is that we can apply momentum. And what is momentum? Is we take the different values of the gradients and we just add some averaging. Okay, and if we add some averaging, we would like to descend over a constant line, a constant trajectory toward the mean. Okay, so I decompose all of my components into orthogonal components, and then I average all of them. Right. So this is what I'm doing. Okay, so I'm taking a certain trajectory, and I'm averaging the trajectory across the different iterations. Very good. So this is the old gradient descent, where we just take the summation of the loss function, the nabla over omega of the loss function. In the new gradient descent, we do this. We take 1 minus alpha, the new gradient, and then we keep a memory. Okay, so we have, when we calculate the gradient, we multiply by alpha, and then we add the memory v, and then we update it with this memory v. Okay, so this v starts from 0, and then on the v we keep accumulating the gradient. Okay, so it's as if you enforce a certain direction, right? You add a certain memory to the gradient process. So this tends to smooth down the variation, like when you do, I don't know, some moving averaging of your function, or when you do some filtering of your signal, let's say. Okay, adaptive learning rate. So of course it's clear that when we are far away from the minimum, we want to move fast, and as when we approach the minimum, we want to move slowly. Of course, we can change the learning rate. Nothing tells us that the learning rate has to be fixed. So what do? We allow large gradients. We allow large steps when you're far away, and then we shrink as we go along. And so what we can do is that we can have the following. We start with a certain value r, and we update this r with the current magnitude of the gradient, and then we update each parameter in the sense that the learning rate is always certain epsilon plus a delta. So these epsilon deltas are a fixed parameter that they sort of decide what is the range, what is the influence of the magnitude of the gradient magnitude on the decrease of the learning rate, and then you sum the square root of the gradient. Okay, so the idea is that when you start off, your accumulated gradients, so the sum of all the gradients is small. So this term is small. So this epsilon can be very large, and this delta has to be, let's say, just 1. Okay. Then as you move ahead with the training, then you're accumulating more and more gradients. So this r grows larger. So this term grows larger. So the effective learning rate also shrinks down. And then you ask me, oh, well, Stefano, how should I choose my epsilon and my delta? And I will tell you, each hyperparameter is a different optimization problem. Okay, so if in order to solve a problem, you have to add a hyperparameter, then you haven't solved the problem. You just move the problem from the original problem to the choice of the hyperparameters. Okay, so if you are trying to solve something and you have a parameter to tune in order to do that, then you haven't solved the problem. Okay, so here my answer is that you have to use your experience, you have to change your training, you have to decide how to fix these values, and the problem of fixing this value is just as difficult as choosing a scheduler from the it's just as difficult as your original problem of choosing down the speed in which the learning rate goes to 0. It's just that now you have baked this problem into 2 parameters instead of a more vague idea of what the decrease should be. Now there is AdaGrad, another optimizer that we really like. We always start from this G, right? This G is our gradient as computed over a certain batch in the data set. So it's clear that we want the learning rate to be inversely proportional to G of I, meaning that when we are far away from the gradient, from the optimal, then we are taking then the gradient is very large because we have a very clear direction in which we have to go to get close to the minimum. But when the minimum is next to us, right, then the gradient should be very small because the function should almost have a 0 curvature, right? So when we approach the minimum, the curvature of the gradient should be 0. So as we approach the minimum, we will also expect the curvature to grow small. So it's clear that the learning rate should be proportional to the inverse of the gradient magnitude. But if you just put it exactly equal to the minimum, then we're back progressing too slowly. So we can choose the value as being 1 over delta plus the magnitude of the gradient. So this is very similar to the previous one. And so we have this adaptive version in which we accumulate the gradients and then we scale it down in a way which is inversely proportional. So this is sometimes too much of a smoothing. So what you can do is that you can add a row that decides how much of the gradient is accumulated with respect to the previous one. So this is slowing down the accumulation of the gradients, and then you repeat the same trick of having epsilon over delta plus square root of Ri. So this is another memory mechanism, but you have another hyperparameter, and you have the epsilon, the delta, and the rho. Okay. So, then RMS prop. So when we do RMS prop, we estimate the momentum like this. Then we estimate the second moment. So first we accumulate the gradient, then we accumulate the gradient square, all with this rho, and then our learning rate is epsilon over delta over square root of 1 over Ri. Okay, so we combine the idea of the momentum with VI and the idea of slowing down the learning rate with this Ri. Of course, many variations of this. I think we don't need to discuss all of them, but basically, yeah, basically this is the deal for today, guys. That's all I wanted to discuss with you. The presentation, I posted it in Slack. Any other question, you guys let me know. Any other question? I really don't know how long we're supposed to do. We're supposed to do 3 hours, guys. I mean, after 2 hours, it's clear that yeah, there is already too much material for my little brain. Okay, any other question, guys? Otherwise, I'm gonna be here as usual. If you have any questions, if somebody still doesn't have a group, or if you hear from somebody that doesn't have a group, let us know. Otherwise, if you want to say hi, say hi. And otherwise, I'll see you next week. Next week, again, I expect a presentation, 20 minutes per group. I think we have 5 groups now. So an hour and a half of presentation, hopefully. Try to have fun. The challenge is fun. And otherwise, that's it. Okay, let me stop the recording. So if you can ask some questions, we say goodbye to the people on YouTube. And we see each other next week.